Okay, so hi everyone. My name is Lily, and for the past 2 months, I've been working on a software project called Thermal Toy Model for Jet Background Reduction. I tried to keep this presentation very broad, very big picture, just because there's so much theory behind the scenes. So for a broader audience, I tried to summarize to the best of my abilities the theory. But in any case, like the most important part of the project was just the software, so I'll try to skip as quickly as possible to the actual results. So essentially beginning with what our group actually studies. So we focus on nuclear physics, and within that, the strong force and the properties that come with it, and something called quark gluon plasma, which I'll define a bit later on. But as always, we begin with the standard model, which currently is our best understanding of the 17 fundamental particles of the universe. And in particular, the strong force is defined by the quarks and the gluon, which is the force carrier for the strong force. So you can think of quarks as the things that make up absolutely everything at the most basic level. They keep things together inside the nucleus. So on the left, I also picture, just for your own reference, a proton, which is made up of 2 up and 1 down quarks. And it's also held together by gluons, again, as a force carrier. So within that broad picture, again, when we have a collision inside all of our colliders, it usually begins with 2 protons colliding, or like you can think of like any particle really, or any 2 nuclei. So they come in and then they undergo the very initial process of part scattering, which is basically the initial momentum transfer between the 2 particles. So this is mostly like where most of the energy goes away. And then it starts a shower of particles, where essentially this creates a whole avalanche of new quarks and new gluons, which interact with one another and create more and more. So this essentially leads to a process of creation of thousands of millions and even billions of low energy particles. And towards the very end, they undergo hadronization, where basically quarks and gluons form other new particles. So for example, protons or neutrons, and towards the very end, they decay into other particles. But bottom line, at the very end, we're able to cluster all these particles into what we call a jet. So broad picture, you can think of a jet as a cone. This is how I like to picture it, where, for example, if you in a collision have 2 particles and they start scattering and showering, you call these showers, you can imagine these showers as a cone-like object. We use jets to study the quark gluon plasma, which I'll define in literally the next slide. But for my purposes, for my software project, the most important thing is that we use a jet algorithm, which allows us to cluster all the particles that we have into essentially groups or different jets that we can then study to better understand the initial collision that took place. And the most common algorithm that we use is called the anti-KT, which essentially picks out the most high momentum particle in the region and then clusters particles around it, but not going into too much detail. Intuitively, you might expect in the collision in pure vacuum to just like see two equal jets in 2 opposite directions, momentum, energy conservation, all of that. But in reality, what we try to study is the quark gluon plasma, which when we hit 2 heavier nuclei, so for example, you can think of lead or gold atoms, they interact, the 2 nuclei interact in such a way that they create a new medium called the quark gluon plasma, which only existed really for the first few microseconds of the universe. And the most important property is that quarks and gluons can exist within the quark gluon plasma in a deconfined state. So that means that usually in particle physics, they cannot exist on their own in nature. But when we collide 2 nuclei in very high energies, we can recreate this initial states of the universe where we have the deconfined state and quarks and gluons can kind of exist on their own. You can think of this QGP medium as just a soup of quarks and gluons for our sakes. And then when our particles or showers of particles, but let's just call them jets, moving on. So when they go through this medium, they interact with it, as you can expect, because it's not vacuum, like you always interact with the medium. So they undergo this process of jet quenching, where essentially they lose a lot of energy while passing through the medium. And in a detector, we only really see the final state of the jets. But when we're able to reconstruct them to the very initial collision, this allows us to study the quark-gluon plasma and recreate the early conditions of the universe at trillions of degrees of temperature. Okay, so now that was a lot of theory in 5 minutes. But moving on to my actual software project, we begin with Pythia particles. For those who don't know, Pythia is essentially a software or a particle collision simulator, which allows us to run thousands and thousands of events at a time, recreating actual experimental data. So it mimics it very closely, and we're able to, from that, take a lot of particle data without actually having data. From then we have our own thermoparticles, which, for our sake, recreate the background in the experiment that we have. So they most closely mimic the quark-gluon plasma that we are trying to study, with certain properties for each particle. And then we also use another software called FastJet, which is a particle clustering or a jet clustering algorithm. Basically, it picks out all the particles and makes jets out of them. So with those three ingredients, I was able to create a toy model to some extent, like pretty closely mimicking real data, recreating the background or the quark-gluon plasma. So the end product was just 1,000 lines of code, more than 40 histograms, and 7 amazing memes, which I decided not to include, and I'm very regretful of that now. Okay, so one last thing that I wanted to mention before going into the actual software is the phi eta detector space. So actually in detector physics, we usually don't use XYZ coordinates. We use phi eta and the z-axis. So you can think of phi as like the very basic cylindrical coordinates, just rotating from 0 to 2 pi. And then eta is defined as the natural logarithm of the tangent of the theta angle between the z-axis and your particle divided by 2. So it's this very complicated definition that basically allows us to go from positive infinity to minus infinity. Essentially in a detector, we are only able to really see between eta of -1 and 1. So this is what I tried to show here, and actually detect particles and jets in that region. And then you can imagine also expanding this space, so essentially unrolling it. And on the right, I just pictured for your own intuition what a bunch of jets would look like in that phi eta space. Oh, and yeah, forgot to mention, eta is called pseudo-rapidity, which is basically a new spatial coordinate that we create just to describe this. Instead of using the eta angle, it ends up being more useful. Okay, so now onto actual data. And trust me, behind background subtraction, there's so many steps going on. I'll try to guide you through all of them in the remaining 5 or so minutes, but I'll summarize it towards the end.
3-minute warning, by the way.
Oh, wait, how is it a 3-minute warning? Okay, never mind. Anyways, I'll be super quick. So we begin with a bunch of Pythia particles that we create through our simulator, and from that we make jets. This is the momentum distribution of all jets that we currently have. As you can see, they fall very steeply, very quickly. So we implement a jet cut that allows us to only pick out the very high momentum jets, because otherwise in an experiment you get very low jets and it's very difficult to study. So for reference, these Pythia jets will be without background contamination, or so-called like pure Pythia jets that we'll later compare to jets with thermal background. Okay, so then we create our thermoparticles with certain distributions. So first, we for every event, we create a certain number of thermoparticles from a Gaussian distribution that we get from experimental data from Alice, from lead-lead collisions. So this is approximately with a mean of 4,000 and a standard deviation of 40. So from basically every event has around like 4,000 thermoparticles. And then the other distributions that we use to create our thermoparticles is an eta distribution between -0.9 and +0.9. So it's a uniform distribution, as you can see, completely flat. Phi distribution from 0 to 2 pi, again, completely flat. And then also a momentum, a PT distribution using this function again, derived from experimental data, which very closely mimics what actual like PT distribution looks like. Okay, so from our Pythia and thermal particles, we create combined jets, which in real data, like you have both like actual particles and thermal particles. So this is what we try to mimic. From FastJet, we can also get the medium background per jet, and we try to subtract it to correct for background in our experiment, which is this very, very tiny portion. So as you can see, most jets are actually have so much thermal background that they're actually hard to read. So we correct for the overall thermal background per event in those PT corrected jets. As you can see, this mimics more closely like the perfectly like very exponentially decreasing slope of our Pythia jets.
30-second one.
Okay, I'll be super quick. So then the idea behind my project is that we can take perpendicular cones from our combined jet, we can rotate it by 90 degrees from the jet axis, and we would see mostly thermal particles, or we would expect to see mostly thermal particles. And then we can subtract those thermal particles from our combined jet to only have Pythia particles towards the end. So this is the process of, in a sense, background subtraction. And the question that we're trying to answer is whether perpendicular cones are a good estimate of the background that we would expect. Okay, so the steps that we covered so far is we generate a bunch of Pythia and thermal particles, we form combined jets, we get the median background, we correct for it per event, and then we do our perpendicular cones from every combined jet just by rotating 90 degrees axis, and then we subtract the momentum spectra of those thermal particles in the perpendicular cone from our combined jet to essentially account for the thermal background that we would expect in experiments. And we would expect this to be only Pythia jets. So now the question is, can we recreate Pythia only jets? Like, how effective is their background subtraction? So the first thing that I wanted to show, and there's nothing particularly exciting about this graph, is just the fast jet media background per event that we get. So this is around 220 GeV per event. So it's quite large, as you can see, and most of our jets are actually uncorrected for. So this is why the very first step is just to correct for thermal background per jet. And then the second thing that I wanted to say was the actual process of subtraction that I described. We begin with our combined jet particles on top, like the purple one. Then we get our perpendicular cone, which again mostly contains thermal particles in the blue one. We subtract the top one from the bottom one to get our subtracted or pure jets. And at the bottom, we have our Pythia pure jets. So what we're trying to compare is essentially our background subtracted jets to our Pythia jets to see how effective our background subtraction actually was. So zooming in on this one, we can see that it was actually pretty close, although not quite. So our current thermal model is not perfect, but accounts for most of the background. Okay, so perpendicular cone method, pretty good, not perfect. So the next step is just to introduce a multiplicative correction factor so that we can get as close as possible to the Pythia pure jets. Okay, so sorry. So the next step is just to fine tune really how we generate our thermal particles to experimental data. Currently, there's so many things imperfect with our distributions. So in reality, the number of thermal particles that we have in an event is not Gaussian. So we can mimic that more closely to experiment. And then the phi distribution is also not uniform. While in my model, we did assume that it followed a uniform distribution. So I included a picture on the left just to show essentially like, instead of having the same number of thermal particles all around the collider, or the detector, actually, it follows this weird shape that we can more closely mimic to experiment. And then the PT distribution, the function that we used can also mimic data more closely to the actual experimentally measured momentum spectra. Also, currently in my experiment, I use all jets instead of just the leading jet, which I think also does not perfectly account for background. And I would like to also, in a sense, double check whether the fast jet medium background that we get is close enough to our thermal model. So we can also manually obtain the medium background just by summing over all the thermal particles that we have in our perpendicular jet. And finally, as I briefly mentioned already, we can introduce a multiplicative factor in the perpendicular cone method, just to more closely mimic Pythia-only jets. So that was so much to cover in 15 minutes, but I'll be willing to take very quick questions. Yeah, as I mentioned, like I spent 2 months on this project. I'm by no means an expert, but it was definitely super interesting to study. And just a few acknowledgements. I would like to thank the overall Wright Lab community. It was super supportive and super fun to be here this summer. And then the Summer Experience Award, which made it even possible for me to be here financially. I would like to thank my PI, Professor Laura Havner, who guided me and answered so many of my silly questions at every point in time. She was always available and always supportive. And everyone else who I worked with, not going to mention them personally, but I'm truly grateful.
Question for Lily.
Yeah, sorry, that was very quick, but happy to go into greater detail.
Yes.
Yeah.
So just, you mentioned that we use eta instead of theta because it goes from -infinity to infinity. And
Yeah.
it was like that function. But there's many functions which could do that. So why that one specific?
That's a great question. And honestly, there are multiple functions in reality that we can use. So instead of pseudo rapidity, we also sometimes use rapidity depending on what is most helpful. So I guess there are different ways to define your detector space, but I think for our NT-KT clustering algorithm, this is the most helpful one.
Any additional questions? I was, no, okay. All right. Seeing none, I want to thank Lily again.